Okay, so continuing where we left off last video, we're going to be doing the same thing with a different function, finding intervals of concavity and points of inflection. So again, we need, before I start finding derivatives, actually, we need the domain of our function. So this function includes a natural logarithm. We know that the domain for natural log is all positive real numbers, and so that will also be the domain for this function. We'll use that in our sign chart a little bit later. So find y prime first. This is a product of two functions, so we need to use our product rule. Derivative of the first function is 3x squared. Leave the second function alone. Plus the first function, x cubed, times the derivative of the second function. So from our generalized logarithm or natural logarithm rule, this is going to be the derivative of 2x, which is 2 over 2x. Remember, that's really just the chain rule in action. This simplifies a little bit, so I have 3x squared natural log of 2x still here. But then these 2's will cancel, leaving a 1 there. And then this x will cancel with that, giving me an x squared. So this becomes plus x squared. Okay, I can now go ahead and find y double prime. So I need the product rule once again, still have a product of functions. So take the derivative of the first function, that's 6x, leave the second function alone, plus the first function, 3x squared times the derivative of that second function, which we already found was 2 over 2x. Plus x squared, I have to take its derivative now. So that's going to become plus 2x. And then notice there is some simplification that happens yet again. We have the 2's canceling out, and then one of these x's cancels with that x. I'm left with 3x times 1, which is just 3x. So I have 6x natural log of 2x plus, now that's, like we said, would become 3x, but then I have a plus 2x here. Combining those like terms gives me a 5x. Okay, now I'm going to go one additional step here because I know that I'm going to be looking for places where this second derivative is either not defined or is equal to 0. And specifically when it's equal to 0, it's easiest to solve if we factor things first. So taking note of the fact that there's an x in each of these terms, I can factor that x out. 6 times the natural log of 2x plus 5. Okay, so is this undefined anywhere? Well, yes, it's undefined anywhere except for the positive real numbers, because again, the natural log function has a domain restriction to just the positive real numbers, but we won't find any partition numbers amongst those, because again, we only get partition numbers from where y double prime is not existent if the original function does exist at those values and is continuous there. But everywhere that my second derivative is not defined, the original function is also not defined. So what that tells me is that the only partition numbers that I will get are from setting this equal to 0 and solving. Okay, so now let's set up our sign chart. Actually, I should solve this first. So I get two solutions from this. One is x equals 0 from this first factor right here, or 6 times the natural log of 2x plus 5 equals 0. So I need to solve this for x to get anywhere. Notice I could subtract 5 and then divide by 6, which gives me the natural log of 2x equals negative 5/6. Remember, to undo the natural log that's happening on this side, I take e to the power of both sides. So now I have a 2x by itself and an e to the negative 5/6 over here. Finally, I can divide by 2. X is equal to e to the negative 5/6 divided by 2. That is my other partition number. So now, making our sign chart, start with your domain. Remember, our sign chart can only include positive real numbers. So 0 is the lower boundary of that interval. I'm going to put it all the way over here as an indication that I can't go any further left than 0. There will be no subintervals over here. Next, I go to my partition numbers. 0 also happened to be one of my partition numbers. It's already there, so I don't need to put it again. aside from 0, I only had one other partition number, e to the negative 5 halves over 2. So what we're going to want to do now is start putting in test values to figure out what's happening to our second derivative here. So remember, we're trying to figure out if our second derivative is either positive or negative on these intervals. I'm going to use this version of my second derivative. So since it's factored, that's going to be the easiest way to go. And I'm going to also just remember that I'm only using positive real numbers because of the domain of this function. So no matter what I plug in for x, this x will always be positive, which means the sign of f double prime is completely determined by what's going on in parentheses here. So let's do this. Let's pick some numbers to try and plug in. I need a test point from way over here. And one thing I know is that if I decrease the exponent on this exponential here, then I'll get a smaller output from this exponential function than I would here. So let's use a smaller exponent. Let's say e to the negative 5. That's less than e to the negative 5 halves, but still over 2 because I don't want to change that part. Okay, what would I get if I plug that into my this little set of parentheses right here? Well, I can do the work down here. 6 times the natural log of 2 times e to the negative 5th power over 2 plus 5. That's what I have in parentheses here after I plug this value in for x. Okay, now the 2's in here are going to cancel, and now I'm left with the natural log of e to the negative 5th. Remember, natural logs cancel those e's, and that leaves me with just negative 5. So this becomes 6 times negative 5 plus 5, which is negative 25. We got a negative value there. Okay. Going the other direction, I can pick a test point from over here. And again, if I just increase this exponent, then I will end up with a larger output than what I got right here from this partition number. So it's negative. Let's just move it up to say 0. If I make it e to the 0 over 2, which is the same thing as 1/2. Let's use 1/2 as our test point. So again, plugging that into the stuff that was in parentheses, 6 times the natural log of 2 times 1/2 plus 5. So 2 times 1/2 is just 1. The natural log of 1 is 0. 6 times 0 is 0, plus 5 is 5. That's positive. So f double prime is positive here. We do get a sign change. Okay. Not only that, the original function is both defined and continuous there because these are functions that are continuous on their domains, and so their product is as well. Putting this information together, I know that this function is concave down where? Well, on this interval right here. Remember, we don't go all the way to negative infinity. We go as low as 0, not including 0. So 0 to e to the negative 5 halves over 2. It's concave up on this other interval here. This one goes from e to the negative 5 halves over 2 all the way to infinity. And then the point of inflection. So for the point of inflection, remember, we have to take this partition number and plug it into the original function all the way up here. So let's do that next. I'm going to box these since that's part of my answer. In fact, let me come back here. I'm going to box these as well, just so it's clear later on where the answers are. Let's do a little bit of work to figure out that point. So I'm taking e to the negative 5 halves over 2 and plugging it in right here to the original function. So that's e to the negative 5 halves over 2 cubed times the natural log of 2 times e to the negative 5 halves over 2. Because again, that's how this function was defined. Okay. So this guy over here, well, actually, let's start here. If I cube this, I'm going to use some exponent properties. So 3 gets multiplied to that exponent right there, giving me e to the negative 15 over 2 over 2 cubed, which is 8, times the natural log of this stuff here. So I'm going to multiply the 2 times this. I get cancellation happening there. That leaves me with the natural log of e to the negative 5/2 power, which, remember, those cancel and leave me with just negative 5/2. Multiplying that completely out, I get negative 5e to the negative 15/2, and then 8 times 2 would be 16. Oh, I shouldn't actually box that, but I did. So that's just the y coordinate of my point of inflection. So point of inflection is e to the negative 5/2 over 2, and then this, negative 5 e to the negative 15/2 over 16. So that's actually the thing I wanted to box. There we go. All right, that was a significantly longer example because the function was a little bit more complicated than a polynomial would be, but it's the same basic idea. All right, let's look at this stuff from a couple different angles here. So in this example, we are not given f of x, but we are given f double prime. And we're asked to find the intervals of concavity and the inflection points of f, but with f double prime given to us. Okay, so this is the same idea. Notice we have a couple of little bits of information here. So first of all, we know f double prime is equal to this product here. And if we're looking for partition numbers of f double prime, I'm either looking for where this is not defined or where it's equal to 0. Now, this is a factored polynomial. It's going to be defined everywhere. So that means that I'm really just looking for where f double prime is equal to 0. X minus 3 times x plus 2 cubed times x plus 7 to the 4th power. Okay, set that equal to 0. And because it's in factored form already, I'm going to get my solutions really easily. X is equal to either 3, negative 2, or negative 7. However, we have this extra information about f right here. F is continuous on its domain of negative infinity to 3, union 3 to infinity. In other words, f is only continuous on the set of all real numbers except for 3. And if f is not continuous at 3, then it's also not differentiable there. And so our second derivative is not defined at x equals 3. Because x equals 3 showed up in my list here, I have to eliminate it because it's not usable as a point of inflection. Now, well, actually, let me back that up. I can still use it as a partition number, but it's not going to be a point of inflection. So maybe I shouldn't eliminate it so quickly. Let's include it, but we just need to remember that it can't give us a point of inflection. Okay. So, all right. So with that, let's create our sign chart so we can figure out our intervals of concavity. And we're going in order from smallest to biggest, so negative 7, negative 2, 3. It gives me 4 subintervals. Okay? We're going to pick test points, plug them in, and see what happens. Now remember, the goal is to plug them directly into f double prime. I just realized something. We can't find inflection points. I needed to eliminate that from the instructions. We're not quite at that point where we're doing that yet, but the reason we can't find points of inflection is because we don't have the original function f of x to plug our x values into once we identify where those partition numbers are. So I won't be able to get y coordinates for those points of inflection. So I'm going to eliminate that. We're just looking for the intervals of concavity. Okay, so coming back to this, we need to pick test points, plug them into the second derivative, which is here, and see if we get positive or negative. Notice that x plus 7 to the 4th power, no matter what I plug in for x here, this will always come out positive because I'm raising it to an even power. So we can effectively ignore this and just pay attention to what's going on with these two terms here. Let's start with x equals, say, negative 10. That's a good test point. So negative 10 minus 3 and negative 10 plus 2 are both negative numbers. When you cube something, it keeps its power. So negative number cubed is negative, positive number cubed is positive. That means what I'm going to have here is a negative times a negative, which is positive. So f double prime is positive here. Let's pick a test point in here. Say x equals negative 4. That's between negative 7 and negative 2. Negative 4 minus 3 is negative. Negative 4 plus 2 is also negative. So negative times negative is positive. We get f double prime is positive there. Okay, let's pick a test point between negative 2 and 3. 0 would work. If I plug a 0 in, I'm going to get negative 3 times positive 2 cubed. So it's negative times positive, which is negative. F double prime is negative here. And then finally, I need a test point that's bigger than 3, say 100. If I plug 100 in, everything will come out positive. So f double prime is positive there. Okay, so now using that information, we're only interested in the intervals of concavity for this problem. So where are we concave up and concave down? Looks like I'm concave up on 3 intervals. So the first one is negative infinity to negative 7. And then from negative 7 to negative 2. We skip this one because we're negative there. And then 3 to infinity. Whereas we are only concave down on this interval from negative 2 to 3. Okay? So another example, but this time what was different about this one is we were given f double prime and we just had to extract the same information, but using only f double prime to work with. Here is another example that we're going to work with. This time we are also looking at f double prime of x, just like the previous example. The difference, though, is that we're not looking at an algebraic representation of that function. We're instead given a graph. So we want to find all of the same stuff. I'm looking for partition numbers of f double prime, intervals of concavity, and x values of any inflection points. Let's start with A. So remember, a partition number of f double prime is any value for which f double prime is either equal to 0 or is undefined. So notice, first of all, at negative 7, we have a hole here and a hole here. There's no point there, so our function is not defined there. That means negative 7 is one of those partition numbers. In addition to that, anywhere that our function crosses the x-axis is where f double prime is equal to 0. And that occurs multiple times in this function. So it occurs at negative 6, it occurs again at negative 2, then at 0, then at 2, and at a couple other points, but before we get there, we also have this vertical asymptote at 3, which indicates that the function is undefined there. So remember, that gives us partition numbers as well, 3. And then we're going to have 4 and 7, both as places where the f double prime is equal to 0. Okay? So that creates a lot of partition numbers. Now what we need are intervals of concavity. So again, concave up, concave down. Let's write those in. Anywhere where f double prime is positive is where f will be concave up. But f double prime is positive for any place on the graph that's above the x-axis. And you'll notice there's a little piece of the graph up here as well. It's positive, it goes horizontally to the left. We're going to just assume it goes all the way to negative infinity. And because it's positive, that's going to be where f is concave up. So I'm going to say negative infinity to 7. Then we're below the x-axis here. So that's going to be where we're concave down. That goes from negative 7 to negative 6. Above the x-axis from negative 6 to negative 2, so we're going to be concave up there, negative 6 to negative 2. Then we're below the x-axis from negative 1 or negative 2 all the way up to 0. So that's going to be negative 2 to 0. We're above the x-axis from 0 to 2, concave up there. Below the x-axis from 2 to 3, concave down there. Above the x-axis from 3 to 4. Below the x-axis from 4 to 7. And then one more time above the x-axis from 7 to infinity. Lots of intervals of concavity there, but very little work needed to find each one because we just investigate the graph. Finally, we need points of inflection, but we can't find points of inflection explicitly. We can only find their x values. And remember, that's going to be any place where concavity changes from positive to negative, where the original function is defined and is continuous. We don't know if f is continuous at x equals -7. Oh, actually, no, I'm sorry, we do know that, because up here it says that f is continuous on its domain of -infinity to 3, union 3 to infinity. So the original function f is continuous everywhere except for 3. So at -7, f double prime does not exist, but we're told that f is continuous there. And we do see a change from concave up to concave down, because f double prime goes from positive to negative. So we do have a change in concavity happening right there at x equals -7. It happens again at x equals -6. Again at x equals -2. Notice this is going to be almost the same list that we gave in part A. It happens again at 0, changed from negative to positive there. Again at 2, it changes from positive to negative there. Now we do not have a point of inflection at 3 because f is not continuous at 3. That's a condition that's necessary for a point of inflection. So we're not going to include 3 in our list, but we will include 4 because there's a change happening there, and then 7 because of the change happening right there. So we do have points of inflection at all of those locations, but I can't really say anything more than that. Okay? All right. Here's another example where we're using a graph to extract a lot of the same information. So notice in this case, we're not looking at the graph of f double prime though. We're looking at the graph of f prime of x. And we're also told some information about f itself. We know that f is continuous everywhere except 7, which is what this interval notation means. So once again, we're doing the same stuff. We're looking for partition numbers of f double prime, intervals of concavity, and x values. But because we're looking at the graph of f prime, we have to think about that differently. So remember, the f double prime is the derivative of f prime. So we have to think in those terms. If I'm looking for partition numbers, I'm looking for where f double prime does not exist, or where f double prime is equal to 0. Now, f double prime will not exist anywhere that f prime is not differentiable, which means discontinuities like what we're seeing here, or corners or cusps. I'm not seeing any corners or cusps, but I am seeing discontinuities in 3 different places. In addition to that, we'll get partition numbers anywhere f double prime is equal to 0. But remember, that's, once again, the derivative of f prime that we're talking about. So we're looking for where f prime's derivative is 0, and that's where we find horizontal tangents. I only see one horizontal tangent right there. Everywhere else seems to not have a horizontal tangent. So putting all of that together, my partition numbers will occur anywhere I have a discontinuity, as well as where any horizontal tangents occur. I'm seeing a discontinuity at x equals 2, horizontal tangent at x equals 5, discontinuity at x equals 7, a vertical asymptote, which is a type of discontinuity, at x equals 11, and then that seems to be all of them. Now we want to look for intervals of concavity. So remember, we can determine concavity by looking for where f double prime is positive or negative. But again, don't forget, we're not looking at the graph of f double prime. We're looking at the graph of f prime. So I have to think, where would the derivative of this graph be positive or negative? And remember, the association between a derivative of a function being positive or negative and the function itself is intervals of increase or decrease. So looking at this, my f prime is decreasing from -infinity all the way to x equals 2. that means that f double prime would have been negative that whole time. And then similarly, there's other intervals where f prime is increasing, which implies f double prime would be positive. So let's find all of those intervals here. Well, concave down, concave up. Our function is concave down anywhere that f prime is decreasing. So that occurs, like we said, from negative infinity to 2 for one of those intervals. From 2 to 5, we see that the function is increasing, and because that's what f prime is, f double prime would have to be negative there, or sorry, positive there, implying concave up. So 2 to 5. Our function is then decreasing from 5 to 7, so that would be concave down. And then it continues decreasing just on a different branch of the function, but from 7 to 11. This is decreasing that whole time, so that's also concave down there, 7 to 11. Okay. Finally, we're increasing from 11 to infinity. That's this entire branch is increasing, so 11 to infinity. Finally, what are the x values of any points of inflection? Well, we cannot have a point of inflection at 7 because, again, the function itself is not continuous there. Points of inflection can only occur at partition numbers, but since we ruled 7 out, the only possibilities are 2, 5, and 11. We need to check for changes in concavity at these values. So for example, if you look at these two intervals here, from negative infinity to 2 and 2 to 5, we switch from concave down to concave up. So at x equals 2, there is a change in concavity happening there. What about 5? Well, from 2 to 5, I'm concave up, and then from 5 to 7, I'm concave down. So once we pass through 5, there's a change in concavity happening there as well. So 5, change in concavity. We ruled out 7, but 11 is another place where we would have a point of inflection because we're changing from, when you go from the interval from 7 to 11, you're concave down, from 11 to infinity, concave up. So as you pass through 11, there's a change in concavity happening there. Those would be the x values of all of my points of inflection for this function. Okay, so this video is long enough, I think. We'll go ahead and stop this one here.